Yeah, let's get started. Welcome everyone to today's Continuous Learning Seminar. Today we are honored to have Professor Nali from Harvard to give us a talk. Professor Nali is a Gordon McKay Professor in Electrical Engineering and Applied Mathematics at Harvard University. She received her undergrad degree from Georgia University in 2007 and PhD degree in Control and Dynamical Systems from California Institute of Technology. And then she was a postdoc at MIT from 2013 to 2014. Her research lies in control, learning, and optimization of network systems, including theory development, algorithm design, and applications to real-world cyber-physical societal systems. She received many rewards, including the ASF Career, the Air Force Office of Scientific Research Young Investigator Award, and ONR Young Investigator Award, the Donald Ekman Award, and the McDonald Mentoring Award. Today, she will tell us about the real-time distributed decision-making in network systems. And if you have any questions, feel free to put in the chat and ask the questions. Without further ado, let's welcome Professor Nali. The floor is yours.
Thank you for the introduction, Guannan. And on behalf of the organizing committee of the Control Mixed Learning Seminar Series, I would like to thank all the audience who have been attending our seminars and also the speakers who have shared their exciting research. So if you have questions or suggestions for the future topics and the speakers, feel free to contact any member in our organizing committee. So today I'm going to share some of our progress in distributed learning and control for network systems. So the talk is a combination of many works, but here are the main contributors from the student and the postdoc. As a small advertisement, so Guannan, who just introduced me, so he will join Carnegie Mellon ECE, and Yang will join UC San Diego ECE as tenure track faculties. So for the student, if you want advisors, feel free to contact them. And Xin, Yujie, Yinyin, so they are senior members in my group, so who will be on the job market next year or in the next couple of years. And I'm also lucky to have both Guan and Xin attending the seminar right now. So if you have questions, so feel free put into the chat window. And I think Guan and Xin will answer the question faster than me. So let's get started. So in the quick motivation of the talk, so in the past decade, we have seen major revolutions in sensing, communication, computation, so which have boosted our ability for real-time monitoring and control of complex systems. So as we look around, we notice there are more and more connected devices, and people claim those devices are smart. So they generate a huge amount of data, and the data is communicated and shared with each other and is processed by powerful computers and advanced algorithms. So people visualize that these connected devices will improve our life quality and make our systems smarter. So we hope to have systems like smart grid, smart transportation, and in general, smart city. But here is one question. Does more connected devices really mean that our systems get smarter and our life gets better? When we look into the reality, it doesn't take us long to realize that we are only at the beginning stage of transforming our system to smarter ones. So here are a couple of examples. Speaking of energy systems, earlier this year, Texas had to go through severe electricity shutdown due to the unexpected winter storm, and millions of people's lives get affected. And then speaking of transportation, so while people are excited about the potential of autonomous driving, we indeed see these self-driving cars have been changing the behavior of human drivers, which might significantly impact the safety of driving. So this news points to the same issue. Having individual smart connected devices is not enough. So we need to figure out how to coordinate, how to make the best use of them. So this motivated the overall theme of this talk. So now let's take a deeper look at the changes from a control perspective, since this is a Control Mixed Learning seminar series. So what's happening right now is that we have more and more sensors that spread out in the system. And the sensors, they can monitor the local situation in real time and pass the data to either the edge devices or the data centers. So the data is shared among different devices and being processed by advanced algorithm of super powerful computers, the decisions is passing back to the edge agents and who taking the physical actions. So like this very powerful picture fit into our feedback control loop nicely. But when we look into the details, like what the challenges, what the changes have been made. So first of all, because we have more and more sensors, and those sensors, they are generating more and more data. Even though we have advanced communication tools, but also technologies are still limited compared with the scale of the systems. And moreover, once we are connecting all the devices, so each active device, they are introducing random fluctuation to the systems, making the system even harder to model and definitely harder to control. So because of those challenges, those changes, as a consequence, like data-driven methods has received lots of attention these days. And this also motivated our control-based learning seminar series. And here, like taking reinforcement learning as an example. So we have been seeing many exciting news about RL in the areas such as Go, video games, and robotics. So such success has been very remarkable in the sense that for those systems, the underlying model indeed is very complex. For example, it's really hard to model the other players' behavior. But RL can just keep playing the game over and over and improving the policy by the state reward observation. So however, when we look into the technology behind the success, so immediately we can see the challenges when we use this method to the societal engineering systems. So the first of all this method require a huge amount of computation and simulations. So it's hard to scale the system to the large physical systems, and that's probably we even don't have simulation available. And secondly, so it's often challenging to provide theoretical guarantees for the cutting edge, practical, complex algorithms, such as like deep reinforcement learning. Like putting all of them together, like a lot of researchers have been discussed, right? Can we use in some special structure? Can we use our prior knowledge and physics to improving those data-driven methods? But here is the question, right? So what kind of special structure, what kind of knowledges that we can really use? For the system I pointed out before, like the energy system, transportation system, indeed, we have been studying those systems for many decades. So we have lots of knowledge about like do the model-based control or just like based on our near experience, how should we do it? But how can we really use those knowledge to improve the data-driven methods? So I just put in some examples that I have been using in our research. Like we talk about the network complex systems. So there's some network structure that is available. And for all those systems, we have some existing like known physics that we know before, and we have some modeling that's available. So can we use them to improving the data-driven method? I have to confess that I don't think it's actually possible to have a universal method that's applied to all different systems. So every physical system has their own special structure and they have different kind of physical rules they need to follow. So in today's talk, I will just give 2 examples to show how additional information can help us. And like the first example is going to be more on abstract level. So we're going to talk about multi-agent reinforcement learning for the network system. And the second one, we're actually going to a little bit more concrete, talk about a real system in practice, like the power system. So how can we using the sensors to helping us improving the existing control in the power system? And in the end, I just want to use these 2 examples to give some ideas, and hopefully you can develop your own like physical-based method, like learning method to improving your system's control design. So now I'm diving into the first part of the talk. So how can we design scalable reinforcement learning method for multi-agent systems? So the overall question I want to ask is this. So as I showed before, for those RL methods, like the typical RL method tend to model the underlying physical system as black box, and then try to improve in the algorithm design. So the question like, can we design the RL for the network systems? But what we're going to show is like, can I just add a little bit of additional knowledge? For example, since I'm talking about network system, can I use in some network structure to improve in the learning? So what do I mean by that? let's look into the model like in your details. So here we have it's a Markov decision process. So we have a stage time that every decision maker need to make a decision at time t. So for each, and we have a group of nodes, and each node stands for one agent. So for each agent has his own local state called Si. So each agent can also take their own local action, AI. So we are looking at the Tableau MDP case where the state and action are found as set. So what the network I'm going to talk about. So we're going to assume there is a local interaction among the agent. So what the local action, the interaction means. So in this kind of problem, we're going to assume for one agent, so his next state is going to depend on his own state and his own action and his neighbor state. So you can definitely, this is the one assumption made in the state transition. I'm going to show you some examples that fit into this local structure. So what's the learning we're going to assume is we're going to assume we know the network structure. So when we say the two agents connected, this means one agent state is going to affect the state transition for the other state, for the other agent. So what we're going to assume is we don't know the particular value of the PI, but we're going to know roughly the connectivity. So once we have the state transition, so each agent has his own local reward. Again, for this local reward, we're going to assume it's only based on his own local state and local action. So what the control policy is, so right now I'm just putting a general framework. So control policy, in the MDP problem, is just take action from the observation, the state. And we're going to assume for this control policy, it's a mapping between the global state to the global action. And we're going to focus on the stochastic policies. So the objective in this talk, we're going to focus on discounting reward, and the gamma here is a discounting factor. So the recent work, we extend the work to the limit averaging case, but I'm going to use the discounting reward case to give you more intuition behind the work. So as I mentioned, there's one key component here is a local interaction. So what kind of system can have the local interaction? So I think you can also think about the system you have in your mind, but this is some examples I'm providing here. So for example, for the epidemic one, so for the epidemic spreading, right, the probability of one agent getting infected will based on the neighbors, the interaction he has, and whether his neighbors get infected. And similarly, for the transportation system, the congestion of a road will depends on the congestion of the nearby roads. So you can model the MDP using the language I provided in previous slides. So now let's look into the problem, what the challenges. So even though I put in the MDP, when you're writing down formulation, it looks follows the standard textbook. But then again, we look into what's the state action space is quickly blows up with increasing number of agents. And taking a simple example, even individuals has only two choices, and as a global system, they're going to have 2 to the power of n choices. And that's really hard even to store all those action and state pairs. So, and definitely people know those methods is hard to analyze. First of all, those MDP has an analysis about computation complexity. So because if we don't do anything, it's going to exponentially blow up with the size of network N. And if we really look into the network case, we can say this is definitely going to be fundamental intractable, and there are very nice fundamental papers talking about what's the class this problem fits into. So then people have been studying, right, what kind of method we can develop, to making the system still learnable to a certain degree. So the different kind of method, for example, I can just pretend I'm just a single learner and all the rest of the agents, just the environment to learn independently, or I can do the linear function approximation or the neural net approximation. But I mentioned, right, it's usually hard to guarantee what's the controller that we eventually learned. So that's the first challenge, it's just hard to really learn the policy if we don't talk about adding any additional structure. And on the other hand, so let me look into the control policy itself. Let's say assuming there is a magical learner and actually learn the global policy, which is optimal in some sense. But for this policy, how are we going to implement that policy? Is the mapping from the global state to the global action. So if for one agent, if he wants to know what's the AI he should take, he needs to know the global state. And imagine the system I putting at the beginning, transportation system, power system, is just difficult to have this information in real time. So this motivates us to look at the local policies. So the local policy I put in the slides is the extreme case, is the fully decentralized policies. What does this mean is ideally, I would like each agent is able to decide what his action based on his local observation, like his local state. So this local policy can be generated to including additional information, right? Rather than just based on my own local state, I'm also taking my action based on my neighboring information. So that's like the math I'm going to present extendable to this neighbor information case. But let's just look at the simple case. Just take action based on my local state observation. So even I'm saying like, I just want to learn a good local policy from my local observation. But then since the state transition still couples everyone, what that means is that if I want to know how good my local policy is, it's actually going to be affected by other people's local policy. So in the long run, so all those local policies are still coupled in a certain way. And what does it mean? It means during the learning process, I still need to share information among the agent. So putting into summary, what's the problem we're trying to solve here is this. So I would like, given the scale of the system, I would like to develop some distributed learning rule. Like the distributed learning going to use some my local state observation, local reward, local communication, and to learn local policies. And I highlight the local here in the learning side because like, what do we mean by local, right? How much information do I have? So this is actually going to become a design parameter we're going to use in the learning algorithm design, right? How much information do we need? And does those information affecting my efficiency of my local policies? So like, this is the problem setting. If you have questions, feel free to ask in the chat window. I hope the problem is clear. And we can discuss like extension after the talk. But as a reminder, so we have the local state transition rules, definite assumptions. We have the local policy, but still need the information to pass it. So now I'm going to do some review about the centralized case. Like, so that's the network case. And let's see, like, if I just grab some method from the RL literature to see, can I apply the method? What challenges we have? So this is the review about the policy gradient in the centralized case. So what that method really means, for those who is not familiar with the method, is a quick review. So typically for those type of method, we're going to parameterize the policy. And the parameter here is a C down. So but once I have the C down, so I can write down my long-term reward, which is a discounting reward in terms of the as a function of the theta parameter. So, but the gradient method, right? Once I have an optimization problem, kind of naturally that I'm going to do my gradient update. But the difficulty for the gradient update is because I don't have my state transition rules. I don't know what the gradient is. So how can I do it? The powerful theorem, the policy gradient theorem is really nice because it connects with my reward observation with my gradient update. So again, you don't need to remember the policy gradient theorem, the equations. The thing I want to highlight is this. The policy gradient theorem, what it's been doing is if I have a way to estimate my expected long-term reward back from the state action pair, then I'm able to compute my policy gradient. So the key component here is a Q function. So the Q function, as I put in here, is called expected long-term reward. Like once I start with my state, and taking my initial action A, and I'm taking my control policy, like the parameter policy, theta. So that is my expected long-term reward. And since we're talking about the finite state action case, you can think about the Q function also as the Q table, right? Because all the S, A are finite. So, and then once we have the Q function, the expected long-term reward, then I'm able to evaluate my gradient through the policy gradient theorem. So based on this policy gradient theorem, different kind of algorithms are being promoted. And this is like one general framework for the Actor-Critic method. So at actor level, we're going to take the gradient update. And in the inner loop level, we're going to estimate the long-term reward by taking the action according to my control policy, using my observation to update my Q function. So this is the like overall picture of the centralized learning. As I mentioned, one thing I want to highlight is the Q function, right? The key elements is the Q table. If you recall, like now when transit system to the network case, my S and A, the exponentially large. And additionally, they need global information. They need everyone's S, everyone's A. So it's very hard to really implement this method. So now let's look into network case. I'm putting a line structure as illustration. So for this one, like what the parameterization we're going to do, because we're talking about local policy, we're going to have a local policy parameterization, theta_i. So the global policy, just putting them together. That's the joint action policy profile. So what the Q function is, so here the Q function is a big Q table for the global system. And I put in the Q function, like writing down the summation, the definition is the expected long-term reward. And since my individual reward R is a summation of individuals reward Ri, so just by exchanging the summation order, so we can have something called individual Q function. So what the individual Q function here is like the expected long-term reward for the individual agent I if the global system starts with as a action pair. Say action pair. So like one thing I highlight here is that even though like from the definition, I can call the Q at the QI as a agent's I's long-term reward. But in order to evaluate, it's going to base on the global state, global A and global theta. And because everything's still coupled in the long run. So like we haven't really solved anything by introducing QI now. So then what's the policy gradient? Because right now I'm doing everyone has an individual theta I, so I only need the partial policy gradient. So the partial gradient, even though it's called the partial gradient, but once I writing down the policy gradient theorem to look at what information is needed, it's need everyone's long-term expected reward, the QJ, I need the summation. So putting summary, like the two challenges we have that still exist here. We need like the table is exponentially large, and for all the steps, it's need the global information. So what should we do? So this is the question posting here, right? As I catch up. So summary, we have a individual agent I here, and we introducing something called individual agent long-term expected reward, but it's need everyone's information. So how can we proceed? Like give you guys like 10 seconds to think about your own method. What are you going to do? So in literature, right, we have been seeing like different kind of method. For example, one popular method, people can do something called the mean field games or mean field theorem to do it, right? So I'm not going to really look into all the individuals information, just try to see some aggregate information. So by here, I'm not going to do the mean field method, and because I didn't really introduce any homogeneous property in this problem, like still all the individual I, PI can be very heterogeneous. So mean field is not really a good tool for the problem I was describing here. So the method we're going to do is actually quite simple. We're just going to do the truncation. So like what the truncation means is this. So as I mentioned, for the individual I, if people ask me to take care of the like entire system, putting a big table, it's impossible for me to keep a large table. So ideally, like when I was making my decision making, I would just look around, okay, who are my friends, who are my neighbors, what they are doing, and I'm just going to maintain some estimation according to my neighbors' information. And how many neighbors I want to choose? That is the design parameter I was talking about before, the K. So if I have a more computation power and more memory, I'm going to put in my K bigger, but otherwise probably I can just make it the K be either 0 or be either 1 or 2, depending on the like choices you can make. So like the question would be, hey, is this method going to work? We just do a simple truncation. The interesting is for the problem I was talking about before, the network MDP, like it looks like general, like capturing all the local interaction. So it has nice property. So what the property means, like we find the exponential decaying property in the model that we described before. So what the exponential decaying property means? So the exponential decaying property, like recall that everything will depend on the Q function, the long-term expected reward. So what this means is for the agent who is really far away from me, like in the network, the network distance. So like even he changed something, like he changed his state, changed his action. So how much is going to change for my evaluation of long-term reward is going to be negligible. And the further it gets, then the effect is getting smaller and it's getting exponentially decaying. So that's what the exponential decaying property means. And the question is, right, does the system really have that? So we can show that for all the MDP problems that I described before, the exponential decaying property holds. And there's a one intuition that everyone probably will quickly have is, yes, you are talking about discounting reward. So by the time when my action affect your reward is already discounted by like k steps. But the thing I want to highlight here is this: the discounting reward, the discounting parameter can actually be strictly smaller than the gamma. And that's why we can extend the result to the limited averaging case. It's a consequence of the net structure, discounting factor, mixing rate, and like some parameter of the P. So if you are interested, like I said, you can put in the question in the chat window, and we can also have some slide to show you like what's the property we need to have to making the rho strictly smaller than the gamma. So because this exponential decaying property, then what does this mean? Is now my truncation, actually doesn't matter what truncation is going to do, like my truncation going to be a good approximation. And I have a design parameter, I can control the approximation, the degree of my neighborhood. I can choose the k equals 0, 1, and how good it is depending on the rho decaying factor we have. So now we kind of solve the first problem, like we have a good approximation by using a smaller table. But now we look at the gradient, right? What the gradients need. As I mentioned, for the full policy gradient, when we compute it, it still needs a global summation. And that still need a lot of like information passing, and how can I have all the information? So the interesting thing, surprisingly, is like when we try to write down, like really doing the expectation, compute like are they correlated, uncorrelated. So turns out for the policy gradient, we can just do the local summation once our Q table becoming like the local Q table. So putting them together, so for the policy gradient, the truncated policy gradient, what we can show is it's going to be a good approximation of the global gradient. And the arrow, again, we can control how small the arrow need to be. So now you can imagine like the rest of the algorithm design can become more straightforward. We can just combine the truncated Q table and the truncated policy gradient to design our scalable IO method. And for the Actor-Critic method, right, I'm putting them as a compare, you can see we're just going to replace all the full information case to the truncated information case. And we are able to show by doing this kind of learning, so the algorithm is going to converge, and we know how good the convergence point is. So I want to highlight some point in this theorem. Hope you guys can see my mouse here. So first of all, like for this hand, we're doing like the guarantee is on the stationary point, like the gradient, how small the gradient is. So this is because the problem, like it's still going to be non-convex. We have a network, it's complicated. So like the property guarantees kind of follow standard non-convex literature. We're going to guarantee the stationary point, how good is it a stationary point. So on this side, we have two components. So one component is a learning rate. So it's going to convert to 0. So the M is the how much actor steps we're going to do. So this convergence rate is consistent in terms of literature, like 1/(m)(m). And this component is the steady state arrow due to the truncation. So what does it mean? Like the algorithm converge, but once the converge point will have arrow compared with the optimal local policy if I don't do the truncation. And then we can, like, there's some other things didn't show here, like, because I guess it will be interesting about how the network going to affect the learning rate and how those parameters. So they're buried in the polynomial 1, polynomial 2. So I will defer that to to the paper. So the thing I want to highlight is this. So even though I say like there's some other parameter in the polynomial 1, polynomial 2, but they are independent of the network size. So, and how the complexity will scales up with the largest state action space set of the k-hop neighbor. So the result means that it doesn't matter how big your system is. So like the really like the arrow, like the row can determine how good your approximation is going to be. And the complexity is just going to depend on how much k-hop neighbor you want to choose. So, and I highlight this one. I will come back to this point later to talk about some new work we have been working on recently. So now this is some simulation result. And for the simulation result, do a very quick overview of this simulation. So but in this simulation, so it's we're doing the multi-access wireless communication. So we have users have packages coming and they need to send to the access point. If the two packages arrive at the access point at the same time, the package got dropped. So this kind of like look at here is fitting to the network NDP setting we talked about before. And when we do the simulation, there's a one benchmark. So that Aloha algorithm is a simple algorithm, but that algorithm indeed using some additional knowledge of the system. So, and look at this, the case that we're talking about, right? If I'm really lazy, I ignore everyone else's action. I just pick my, just look at my own state doing my learning. It still can outperform the Aloha algorithm. If I try to add it one step neighbors, so it can keep improving. So, but again, I want to highlight one thing is about the complexity. So even though the ultimate goal is to control the complexity of the algorithm, so once we test the algorithm into network case, still unavoidable because even for two agents, you can still have a larger state action pair and the cursive dimension from MDB, still making the method slow. So even though this is already a good algorithm scalable to the large system, but I want you to pay attention to this large sample complexity. So that's kind of why it's motivated us further to think about for the real system, right? What additional things we can do, right? Are we really going to use this algorithm as an online algorithm for the real system, or should we do additional things? So as a summary, so what I have been showing for the first part of the talk is this. So we tackle one challenge is how can we making sure we have a learning algorithm that can scale up to the large system. So the approaches we've been developing is really based on the nice property from the system as an exponential decaying property. And I also want to say exponential decaying property is not just it's not a new property that we discover in our problem. So in general, the network control papers and some other network connectivity papers. So people also see the exponential decaying property in a broader class of systems. But because exponential decaying property, so we can design different kind of method. The method I present before, it's just one method, right? Once you have the truncated Q-function, you actually can do some other algorithm design using the cutting edge reinforcement learning, doing the deep IO, you can change the parameterization to do better. So that's why there's a lot of ongoing and future work. So as I mentioned, we already extend the work to the average case and other ongoing work doing the function approximation, and then try combine the techniques with other IO method. And another thing I want to say is the other multi-agent IO method. So that's going to be next slide. But before that, I probably want to pause a little bit to see whether has a question in the chat window.
Yeah, there's two quick questions. I guess the first question is from Adnan. It says, based on this method, the next state of agent I, when he takes the local action, will be its next local observation. Does the question make sense to you?
So I think for this learning algorithm for here, we're assuming, so we know the state SI and AI. And for the learning algorithm, if I decide the K-hop neighbor, for example, K equal 1, so that's also assuming I can observe in my neighbor's next state. So I think then my answer will be yes.
Okay, and there's another question. In the example you gave, what is the reward?
The reward is the package loss. For this one, the example for this one, when the two packages are at the same time, then the package will drop. So then the reward is about you could say the negative of the drop rate, or how much the throughout of the system.
Okay.
Yes.
Yeah. Yes.
But you can clarify me if I'm wrong. So that's my understanding. How the hop is defined here, multi-dimension space. Is this question for this example? Yeah,
I'm not sure either. Oh, he said yes.
So the hop here. So when we say one hop, for example, for this case, so since these four agents, they can access to the same point, because that means their action will affect each other. If they send in the package at the same time, the package will drop. So they are connected. That means one hop. For this person. And then if you take this agent, then his neighbor, depending who are the access point he has and who can access to the same access point will be his hop. So that's why when I put in here, we want the K equal 1. So it's still the size of the K hop neighbor is actually also grow quickly. Yeah, does that answer your question for the hops? Okay, great. Good. So I'm come back to other multi-agent IO setting, because as I mentioned, I hope the talk is more motivating you to think about different problems. So this is we actually also did some other multi-agent IO setting, because I do think in the multi-agent IO, the first important problem is to ask the question, like what are the right question for different application. So this is another setting is a continuous state, continuous action space. And like we assuming the model is linear dynamics, then we can do analysis. So for this one, we actually removed many assumptions and we just want to see what we can do. So you look at here, we didn't assume like, even though in our back mind is a network system, but we didn't make assumptions on the network case, like what AB will look like. We didn't make those assumptions. And also for the cost, because sometimes the cost is not just based on your own state or your own control action. It can be like coupled. So we, again, just assuming individual, they observe a certain portion of the cost, but it can depending on the global state, global action. So the control policy, right? This is because we talk about network case, we want the control policy can be implemented in practice. So it's going to be based on the information that's available. I put in the I here. So that means depending on your information infrastructure, so you can specify what kind of information you can have when you decide your real-time controller. And so far for this one, we focus on the static controller, just KI, but this one you can extend to the dynamic controller like the LQG case. So we actually had to work on this general setting, and the application we have in the paper is about thermal control in the building, right? So this is how the thermal, like telling how the thermal dynamics have been affecting each other at different zone. And the quadratic cost for this one, probably the cost function will be just the comfort and the power consumption. And the control policy, right? Depending on what information you want to put in, like for one zone. And this is, by the way, our new building. So I'm in my new building, it's really big. So I think that's a good motivation to study this problem. Like this, I'm not going to talk about details, what exactly we did. I just want to highlight the difference, right? You can see here, we didn't make those assumptions. So, and then the algorithm we're doing is also different. We didn't do the Actor-Critic with and the policy grading we have been doing, we're doing the zeroth order method. I will come back to zeroth order method later on. So, like this is one difficulty every time we're talking about continuous state, continuous action is about stability. So for this one, we have some stability guarantee with high probability, and then we can show the sample complexity for these algorithms. But so like if you're interested, feel free to read this paper. But what I want to pose a question is this question. So like, as I mentioned, for the performance guarantee we have for the one I presented before and also this work is show how the station, like how the gradient have been decreasing, right? So we can see, okay, if it converges, it converts to a stationary point. But for this kind of cases, right, for the LQR, for the centralized case, we know it's going to be optimal if I do the policy gradient, that's a stationary point. But now I have the information constraint since getting changed. So what exactly those convergence point for those learning algorithms? Like even though I say I have a learning algorithm will converge, but what are those convergent points? So that's actually motivated us to look into the optimization landscape. Like as the first step, we didn't really focus on the multi-agent. We just grabbed the one uniqueness of this problem is a partial observation. So like we look into the standard textbook LQG problem, and here the LQG I really mean the partial observed linear system, and try to understand, so what's the optimization landscape? So it's a like very recent paper. I would like to say the message is mixed. So we have some positive findings, we also have some negative result. And still there are many things we know the structure, but we still, it's still like a work we're trying to understand how can we use this method, this understanding to develop meaningful learning, efficient learning method. And similarly, like once we put in those, even in general, the multi-agent MDP setting, we also have something interesting finding. Hope we can have some result like in a few months. So if you're interested, like feel free to read, and I'm happy to discuss offline after the talk. Okay, that's the first of all the work about the multi-agent and talking about more general modeling structure. So the next topic I'm going to focus on, I'm going to talk about a concrete like system, right? So because all those data-driven methods is motivated by the real, like at the power system, transportation system, other different type of systems. So while if I really want to see, can I really apply some method to those one, what method should we have? So I'm going to talk about voltage control as the example. So which is a recent work we just finished, like I think last month. So what's a voltage control problem? So most of you probably not familiar with it. Just a quick introduction. So the volt, like in the power system, the goal is to transmit the power through generator to the end users. So in the distribution, like talking about voltage control in the distribution level, So there is power electronics making sure at the feeder level, the voltage is maintained as the like nominal value. So this PU means per unit, like the nominal value. And if like in our like 110 voltage, like that's kind of the nominal value, and at this end, so like that's the setting people have been using. So what's happening, like the voltage will change according to the system loading condition. So when we have a load, so this power flow goes to the load, and then the voltage will drop. And once now we have more and more generations, like renewable generations in the distribution level, so those reverse power flow can increase the voltages. And like everyone had some experience, if your electricity is not really maintained well, like even your computer will have fluctuations. So that's why, like, to making sure all the electrical appliance can work in nicely, we have a like higher limit and lower limit. We try to making sure the voltage most of the time will stay in the region to protect the system. So the objective is, then there are some controllers down in the system. And so can we using those controller, like you can do the power injection, as it's like, so I can consume more power, I can inject more power into the system to making sure the overall voltage stay in the safe region. So that's the problem. So let me put in the control feedback loop. What this means, right? Given the system control, like the uncontrollable loads, they're controllable loads. So then there will be voltages at the entire system. And the voltage, what will determine the voltage? That's the physics. That's the power flow equations. And like, so once you decide what your generation and loading condition, you will have voltages and people can measure that. So what the control problem is, right? I have some controllable load, I can change it. So can I change my load according to my measurement? If I see something wrong, I take some action to making sure my system come back to the good region. So that's the voltage control problem. And what's the difficulty of it? So there's a lot of modeling, like in power industry, in the transmission side, but in the distribution side, because typically it was like in the low voltage and it's also like really large number. So there's not really much modeling. Like we know the physics, but there's not much modeling of that system. What do I mean by that? So the network topology, right? Even the connectivity. So most of connectivity we know, but some connectivity is hard to know. Even if you can think about your house, I'm renovating my own house right now. It's impossible for me to really figure out what's exactly the connection behind the plugs, because I've been like 60 years old, who knows what other people have been doing it. So that's a big problem for us right now, right? So it's hard to know the network topology, and then what exactly the parameter of those network. It's like, we don't have those data. And there's other situations that we would like making sure the system can run in real time in the feedback way. So, and that's the difficulty I put in here, right? If I'm doing the data driven, I want to solve this issue because I don't have a good model for the voltage. Like I know they're connected, but I don't know how the X exactly determine the V. So that's the question. So now let me to put into the like all the description into the mathematical form. So like we have distribution network, like some node we can control, some node we cannot control, and then some part I can put in monitor to monitor how good the voltage is. So that's what I call monitor node, controllable loads. So the optimal voltage control problem, as I was describing before, has this element. So first, when I control those controllable loads, there will be cost associated. I want to minimize the cost. And so there will be, like for each appliance, when I try to control it, it's a physical appliance. So there's a physical constraint I cannot violate. For example, like the power injection is always have a lower bound and an upper bound. And there's another part, this is a system model. Once I decide my controllable power injection, so then that's the voltage I can measure, but it's very hard to model that for the exact equation. So what's the requirement for my control requirement? Is it, so first of all, as I mentioned, typically voltage, it's actually impossible to making sure the voltage always satisfy that. So the voltage constraint, like is asymptotically or most of the time, I want the voltage stay in the safe region. And this is the action. So for the control action, I want the control means the control action should satisfy the hard constraint. And the probability and additional things, I don't have information of the V. I want my controller can do some model free. So I hope the problem is clear in the high level. So now what's the algorithm being using? That's the point I want to make, is because I have been working on the voltage control for many years. So I know if I know the voltage model, I know how to do it. So this is the way, like this is the one way that we have been doing it. So this is the optimization problem, even this optimization problem, but I want to design a control feedback loop. So the way I'm going to design it, I have the saddle, I change this one to be a saddle point, put in the constraint as the objective function, and then I can using some method. So the method for this talk, so we talk about projected primary dual gradient method. So for the method, what I want to say like is on the high level intuitive, it's just like for each one, this is my saddle point problem. I'm just doing the gradient descent. But in order making sure the constraint be always satisfied, I'm doing the projection. And there's some question you probably want to ask, why is this kind of like projection? So this is a continuous time. So there's more discussion about why we pick this projection, but this projected primary dual algorithm allow us to satisfy the voltage constraint all the time, and also allow us to show the voltage is going to asymptotically convert to the point. So like looking at this algorithm, why is it a feedback control algorithm? This one. So I don't really need the modeling or other information. What this algorithm is doing is I can have the voltage measurement, this is kind of the measurement, and then try to decide some computational variables, and those variables will tell me how can I take my control action. And like how this V coming from, it's coming from the system itself. But there's a one difficulty, right? The voltage, as I mentioned here, is I can just measure it. I know the voltage, but the difficulty is this guy. When I try to compute my control action, even though if I assuming I know my cost function, because that's my own cost function, I can decide it. But I need to know, should I go up or go lower based on how my action affecting the voltage? As I mentioned, it's actually hard in the like whole distribution system. Once I take a small action, given the current system, like the situation, is am I like really increasing that voltage at one node or decreasing the voltage at the other node, and how much it has been changing the other node? So that's the major difficulty in this one when I apply the algorithm in practice. I don't have much of this information, and I need this information. And this information, like in the modeling structure, this will depend on the parameter, the resistance, reactance of the network, but we don't have those parameters. How can we do it? So some of you, I think, probably familiar with those zero order methods that people have been talking about a lot recently. So I'm giving you a quick like overview of the zero order method, what I've been doing. So for the zero order estimation, because right now I just need the gradient information. Right? All the other information still be fine. I just need the gradient information. So simplest gradient estimation is just do the 2-point, the finite difference approximation. So here the S is a perturbation. So I can just like using this finite difference to approximate the gradient. But since I was talking about we doing the real-time control, right? So how can I really like control all the rest of the system and just run to point? It's hard. So that's the use of single point estimator. I'm just doing one perturbation and using this approximation as my gradient estimation. So this is a high level of the how can I estimate the gradient without really knowing the gradient, without really knowing the function structure. So, but like this is taking those like perturbation from the optimization or learning community doing the random approximation. The algorithm I showed before, we have been like focused on the continuous time because this continuous time has like more to, at least for us, we know more tools to study the stability, to study the like convergence of the system. So we were talking about the continuous time algorithm. So for the continuous time algorithm in the control field, we have something very similar. It's extremely seeking control. So for the extremely seeking dynamics, I put in here, you can compare them. The single point gradient estimator, this is the random perturbation, and this perturbation is the sine source signal perturbation. And all the rest, they are similarly. Look at here. This is how much you want to perturb. This is how much you want to perturb. The analysis tool, that's still something we are still learning right now. Like we know the tool for two sides, but what the connection between them is still our ongoing work. For this extremely seeking control, for the analysis, what people have been doing is to looking at the average system around within the period. So then the average system will perform like the gradient descent under those assumptions. Then by the perturbation theorem, we can show that this system is similarly to the average system, and like the analysis from the average system can apply to the extremely seeking system dynamics with certain perturbation, with the perturbation theorem. And furthermore, because in practice, we don't want to see too much fluctuation in real life. So we can continue to add like other filter, like this is the one example called low pass filter. So we can do low pass filter to smoothing the dynamics. Because like if this one I put in here, large omega, so it's well like fluctuating a lot. If I want to see the system has a smoother behave, I can add a low pass filter. So that's the nice thing from the control community. Like we have understanding how can we change like redesign the dynamics by using different kind of filter design. So now back to here, right? It's becoming straightforward for the control, like the data-driven voltage control. This is the only information I don't have. So when I'm going to do it, I will just add a small perturbation signal to my action. So this is my power injection action, adding some small perturbation. And this for this one, we're going to use the sine of perturbation. And then when I try to estimate the voltage derivative, so I'm just going to use the low pass filter version to estimate the voltage derivative. So putting them together, right? This is eventually the algorithm has to look like. So this is the original, like if I have model-based algorithm, and this is something I don't know the voltage model. How can I do it? Right. So I will build estimation of the voltage measurement and the voltage derivative. And then I can replace all those derivatives and the voltages with my estimation. So intuitively, the method will work. And like it can also tell us how can we really implement it, right? So we have like, this is some details about how to implement it. We have monitoring bus and we have controllable bus. As a monitor bus, I'm going to take the measurement, put in here. Like if certain nodes can monitoring, so it's a monitor the voltage and share with other nodes. Is your screen okay? My screen is flashing right now. Hope it's fine.
It's okay.
Okay, so and this additional variables is just for the exchange of like the information. So once they're doing that, taking the action. So the nice thing for this algorithm right now, like we can guarantee optimality and it's really model free and it's adaptive because if the system changes, the voltage and also the voltage derivative will automatically change. And I put in the decentralized quote here is, so here the decentralized, what do we mean is that for each node, what action you should take, you can do plug in, like, so plug and play fashion. So like, again, there's some ongoing future work is how can we even make this information sharing to be more like local rather than like through the cloud, everyone share the information. So even though I was mentioning the method is very intuitive, the analysis is actually not. So if you want to know how do we handle the physical constraint and also model free and making sure they align with each other. So this is our recent CDC paper. So feel free and you can ask us questions about the proofs. So it's for me, it's also a good learning experience to learn the other tool, how people prove in the convergence. But I want to say is this. So we can show the method, the model-free method is asymptotic stable, and it's something called practical asymptotic stable, means that some parameter you can change and the method will still going to work if the parameter is stay in certain bound. And it's because it's model-free and when we design the algorithm, we make sure the algorithm has robustness. So the algorithm is robust. So even you have measurement noise or something parameter is a bit wrong, the method is still going to work. And you can, let me use the simulation to show it's actually convincing. So for the simulation, even the analysis made some assumptions. So in the simulation, we actually did the full non-convex AC power flow model, like to determine, finding the mapping between the power injection and the voltage. And we have like monitoring bus, we have the control bus, so and we have generation, the load. So look at the simulation here. So this is so we run the system in real time design. So this is the PV generation. And we just keep doing our control, like build the controller into the system and making the system going to react like adaptive to the system situation. You can compare. So without voltage control, so the voltage, because there's too much PV generation, the voltage will exceed the upper limit with the voltage control. So like over most of the time, it works very well. And like this, as I mentioned, right, because it's still feedback sense, like, so it has some fluctuation once something wrong happened initially, but then most of the time it works pretty well. And we also try to add in noise into it. It's quite interesting and I would say impressive. Like you can actually add a big amount of noise and the performance overall still perform very well. So what this means like is didn't really require us to have a very advanced sensing. It's good in terms of convincing people to implement the algorithm. So putting in summary, so for this example, what I'm showing here is this. So what we have been doing in the model-free data-driven method, right? It's not just grab, it's more like from bottom to up method, right? Understand what method we actually already have. And then for the new system, right, what things we don't have, and then to just design the learning part for the part that we don't know. And like by doing that, it's saving a lot of like sensing, and the algorithm perform like much faster in terms of just like do the learning from beginning. So like there's a lot of future work in terms of like practice is like, as I mentioned, how can I further reduce the communication needs? And so the algorithm is continuous time. So in practice, I will still taking action, not continuous time, going to be discrete time, how those things going to affect it. And there are many other practical implementation issues. And like I'm like looking forward to collaborate with the power industry people more to test the algorithm. And then I also want to show some advertisement for our recent work, as like the work had been like on my webpage, you can look at here. The another one I want to say is this. So I've been, so Guannan, Xin, also part of the author. So we have been like looking into the IO method. I want to know whether the IO method is good method for the power system. So in the last year, we actually spending long time trying to go through all those existing literature in terms of data-driven learning decision-making method for power system. So we finish a review paper, and I hope the review paper will be useful for the students who are interested in this topic. So in the end, so I'm close, like at the end, the last slides of my talk. So I'm kind of just show you two examples, and one is in a more abstract level, the other one is more concrete level, and to talk about how can we design the efficient data-driven method. And there are a lot of like questions or challenges, right, depending on the systems. So what will be the right method for the certain application? Still need a lot of like interdisciplinary collaboration between people across different fields. If you are interested in those questions, feel free to contact me and contact anyone like who has been involved in this work. Thank you.
Thank you, Lina. Very nice talk. So we are short in time, so we can still maybe take a few quick questions. If any questions, you can directly unmute yourself and ask the question. There's one question in the chat. For example, 2, would you express based on what criteria you choose the monitoring bus?
So good question. For this work, we haven't really done to that stage yet. So we're just kind of assuming the infrastructure is already given to us. There is monitoring bus, controllable bus, and then under this kind of bus, what we can do. So the next level definitely will be, hey, then where should we put in the monitoring? Where should we put in the controllable bus there? And that question will be very interesting and useful to study, because there is a controllability question and an observable question in the network, but we haven't really looked into that yet. Yeah, good question. Thank you.
Yeah, thanks. I have a quick question. So for the second part, because everything is in continuous time, how do you see in practical implementation, how can this more continuous time type of thing be implemented on the hardware?
I believe when Xin run the simulation, even the simulation is run in the discrete time. So so it's like in practice, it should be run in discrete time, because my control action and monitoring, right, you cannot really do the continuous monitoring, really continuous time. And once we put into the discrete time, there's actually other research question going is how big the discretization should be, and we don't have the answer for those yet. And indeed, they are important questions to making sure the method work in practice.
Okay, great. Is there any other questions? Quick questions? Okay. Yeah, if there's no questions, let's thank the speaker, Professor Li, again. And thank you all for coming to today's seminar. And next week, we will have Professor MF-OVC from University of Michigan. So see you next week. And thanks again, Professor Li. Thanks again, Lina.
Thank you, everyone.
Thank you.